Hello, assalamu alaikum. Today we are going to talk about the most interesting chapter in linear algebra, which is called vector spaces. Vector spaces. Vector spaces, basically it is the core of this course in linear algebra. Okay, so it has many interesting ideas that you need to focus on. Once you get this chapter, then you are in good shape in this course of linear algebra. Okay, and the idea here is we mimic what you know about vectors from your physics courses, and we build here kind of abstract structure that we can use to generalize the concept of vectors. Okay, so for example, you know in physics when you are talking about something like acceleration or force, then it is represented by magnitude and direction. So the magnitude is the length, and the direction you can take it any way you want. Then you understand, or you can see here if you are talking about force, and then you know how to add or subtract force, correct? So here you have vectors, and you have here an operation called addition. Also, when you have a vector like force and you multiply this by scalar, you know what is the meaning of that. Okay, so that is something not new to you. You used to do it in your general physics 1. Well, now we want to generalize this. So we need to think about here a set of objects. A set of objects. Let's call it V. And in this set, we have an operation. We call it addition. And here we glue with this the set of real numbers, or complex numbers if you wish, but here we are going to focus and consider only real numbers. Okay? And here we need to consider the multiplication of a scalar by a vector. This is what you used to do in your physics courses. Okay? So now what do we want? We want certain conditions to be satisfied, which is actually we mimic what we have in the classical sense that you used to do. So number 1, we want U plus V to be in capital V for all U, V, in V. So any two objects here you take, their sum should be also an object in the same set. Of course, here our set has to be non-empty because it doesn't make sense to start working on an empty set. Okay, so here this set V is not empty. Okay, 2, we want U plus V to be the same as V plus U, again for all U and V in V. 3, this is what we call the commutativity. Okay, we want U plus V plus W, whether you do V plus W first or you do U plus V first. We want that to be the same. So here for all U, V, W, and V. And maybe here I'll write it again for all U, V, and capital V. 2, 3, 4. There exists a zero object. There exists a vector 0. So here, if you take force and add a 0 force here, the result is F, correct? So we want that. So there exists a zero object. Let me now erase this. There exists a zero object. Let me make it here capital 0, or just to stress that this is a zero object. It's not the zero number that you know from your first grade math. The zero object such that 0 plus U equals U for all U belongs to V. Number 5, for each U belongs to V, there exists negative u belongs to v such that u plus negative u is the zero object. So for each vector you take, there is something like the opposite, where when you add them, you get the zero vector, or the zero object. So here, in those 5 conditions, I am focusing on the addition, okay? Now, again here, maybe it is good to stress that this addition here, it is an operation you define, okay? It doesn't mean here I'm talking about the addition that you know from your first grade math. It is an operation you define that will satisfy those 5 conditions, okay? All right, now, number 6. We are going to focus now on the scalars when you multiply them by the vectors. So here, k for each, k in R and u in V, we must have ku belongs to V. And you know, when you have a vector and you multiply that by a scalar, it is like you stretch it or you shrink it, correct? Still, what you have is a vector. All right. Number 7. If you multiply k by 2 vectors u plus v, that should be the same as ku plus kv. Again, for all k in R and uv in v. Number 8, we want k1 plus k2 multiplied by u to be the same as k1u plus k2u. So here you have the sum of 2 scalars, then you multiply by a vector. That should be the same as if you multiply the vector by the first scalar, the vector by the second scalar, and you add them. Again, for all k1, k2 in R, and u in V. 9. If you have k1, k2 multiplied by u, and you do the scalars first, that should be the same as if you do this first and then multiply by the second scalar. And number 10, the scalar 1 multiplied by the vector u should be u for all u belongs to v. So as you can see here, those 5 are related to the multiplication by scalar, and those 5 are related to the addition of vectors. Okay? So, any set of objects with 2 operations, addition and scalar multiplication, that satisfies those 2 conditions, we call it a vector space. Okay? All right, let's start by an example here. Let's take R2. And what do we mean by R2? We mean by R2 all matrices of this form. A, B belongs to R. So here are all 2 by 1 matrices. Now, this, if you think about it, this is actually what you used to write in physics as AI plus BJ. So AI plus BJ in physics, you like to write it like this, but here we like to write it A, B in this matrix form. Okay, and you will see in a minute why we find this is convenient, okay? Because if we go in higher dimension, we can keep going, but here, then that is good for 2 dimension, for R2 or for R3. Okay, so here, how to define addition? Addition of matrices. How to define multiplication by scalar? It is what you know about matrices. K into AB A matrix you multiply by scalar. So that is K, A, K, B. Okay? So here we have V, and we have this addition, and we have this scalar multiplication. So we have a set of objects, we have two operations. Now the question is, are those 10 conditions satisfied? Well, we'll quickly go over them one by one because this is very easy and we know they are satisfied. Okay? By the way, this sometimes we write it like this. A, B. So instead of writing your objects or your vectors 2 by 1, we can write them also 1 by 2. Or sometimes we write them like this, A, B. So whether we write them like this or like this or like this, still we are talking about the same thing. Okay? So that should not confuse you. All right. So let's think about the first one. If I take two objects or two vectors in my set and I add them, how do we add? We add here, let me clarify that. Let U equals A1, B1. V equals A2, B2. What is U plus V? This is going to be addition of matrices, correct? So this is A1 plus A2, B1 plus B2. And now you think about this as one number, this as one number. So it belongs to R2. So the first condition here, it is valid. Look at this one also. U plus V, V plus U. Well, U plus V, V plus U, you need to swap those. So still get the same thing. It is in V or in R2, correct? So here, condition number 2 is also obviously satisfied. So I don't need to write it. 3, associativity here. If we take U, V, and W, it narrows down to associativity between real numbers. And that is also valid. Number 4, so here number 3, that is also easy. Number 3. Now, number 4, what about the zero object here? Well, we want something when we add it to AB, we get AB. So the zero object here is the zero matrix or the zero column matrix. Because this plus AB will give you AB. So here 4 is also satisfied. What about number 5? For each U, 5. For each U, there is negative U. When you add them, what do you get? You get the zero object. Number 5 is valid. So here the first 5 conditions, they are obviously satisfied. What about number 6 here? You take a vector U, you multiply it by K, what do you get? You still get a vector in R2 or in V. So number 6 here, also valid. What about number 7? I'll leave it for you. Double check that. Obviously satisfied. What about number 8? Obviously satisfied. What about number 9? Obviously satisfied. What about number 10? 1 times U. Take K to be 1, you get what you have. So you have all 10 conditions satisfied. And maybe now you are thinking, well, that is trivial, so why do we need to worry about that? Well, remember here, I'm starting by a very trivial example, which actually I know you already know. But now we want to generalize this into something that is more sophisticated, okay? And now my question to you, if I come here and I change my example and I make it instead of R2, R3 here, or R4. So if I go here and I change this and I make it like this, A, B, C, such that A, B, C in R. So this is R3. The same addition, the same multiplication or scalar multiplication. So go over them one by one. You find all the conditions satisfied. In fact, even if you generalize this into Rn, A1, A2, An, such that A1, A2, An in R. The same conditions are satisfied, and as we did here for R2, you can trace that and find that all of them are satisfied. Okay? So this vector space is the most simple vector space, and that is called the Euclidean vector space. Okay? So that's you can consider all of those. So here, no matter what is n equals 1, n equals 2, n equals 3, n equals 100. So those family of examples. Okay? Now I'm going to take here another example. 2. Okay, let me again make it simple. My V is all 2 by 2 matrices. Again here, my addition is matrix addition. And my scalar multiplication is multiplication of a matrix by scalar. So let's go over those. Again, quickly we can do that. If you add 2 by 2 matrices, what do you get? You get a 2 by 2 matrix. We know that. The first one is satisfied. If you add a matrix U plus V, it is the same as if you add V plus U. 3. If you have 3 matrices, you know from chapter 1. It doesn't matter which 2 you add first, still it is the same. 3. It is satisfied. 4. 4. What's the zero object here? Let me write that down. What is the zero object here? It is the 0 2 by 2 matrix. This is what we mean by the zero object or the zero vector. Right? Number 5. For each 2 by 2 matrix, A11, A12, A21, A22, you take the negative of that, which is negative A11, negative A12, negative A21, negative A22, and when you add, what do you get? You get the zero matrix. So here the first 5 conditions, they are satisfied. What about the next 5 conditions? So if you take a 2 by 2 matrix and you multiply it by scalar, remember when you multiply a matrix by scalar, it means you multiply each entry in that matrix by the scalar, correct? So you are going to get here K A11, K A12, K A21, K A22. So that is still a 2 by 2 matrix. So number 6 is satisfied. Number 7. You add 2 matrices, then you multiply by K. That is the same as if you multiply each one of them by K and you add. So those conditions, we discussed them when we learned how to add or multiply a matrix by a number. Okay? So all of them are satisfied. 5, 6, 7, 8, 9, 10. Okay? All right. What if I change this into 3 by 3 matrices, or 4 by 4 matrices, or m by n matrices? So here, if I go back and I change this and make it all m by n matrices, and the same thing, addition of matrices and multiplication of a matrix by scalar. Are we going to get anything different here? Everything stays the same. Okay? The zero matrix will be the zero matrix of size m by n. But everything is valid. So here you have another family of examples. This family, we call it m by n. So from now on, when we talk about this family of vector spaces, we use here m by n. And here we use Rn. Okay? All right. 3. Let's talk about polynomials. So those kind of trivial. Let's talk about polynomials. Take your V to be all polynomials of degree 2. What do we mean by polynomial of degree 2? Recall that. Polynomial of degree 2, it means V is going to be all polynomials a plus bx plus cx squared, such that c is not 0. C is not 0. In this case, we guarantee it is degree 2. Correct? Is this a vector space if we consider here addition of polynomials or functions? And the multiplication here, you multiply your function by a number. Multiplication by a number. Which is what you know from pre-calculus. You know if you want to multiply this by a number, what happens? You multiply each term by that number. Okay? Is this a vector space? Let's think about it. What happens to the first condition? If you take two polynomials of degree 2 and you add them, are you going to get a polynomial of degree 2? So in other words, is it closed under addition? No, it is not a vector space. Why? Well, all you need is just to take one of those conditions and say this condition is not valid. Okay? If you want to say something is not a vector space, you don't need to check all 10 conditions. All you need is just to take one condition and say this condition is not valid, and here it is. Bx equals negative x squared. Qx is x squared. Degree 2, degree 2. What happens when you add them? It's the zero polynomial. Is the zero polynomial here? It is not a polynomial of degree 2, so that doesn't belong to V. So this is not a vector space. And now the question is, if I want to make it a nice vector space, what should I do? If instead of saying all polynomials of degree 2, if I say all polynomials of degree less than or equal to 2. So if I fix it 2, it is not going to be a vector space. Now what happens if I come here and I change that and I make it here less than or equal to 2? So in that case, I don't need to say C is not 0. C could be 0. So all I need is just to say A, B, C are real numbers. So in this case, think about those 10 conditions. If you add two polynomials of degree at most 2, what do you get? You get a polynomial of degree at most 2. So this is valid. If you add two polynomials, P plus Q, that is the same as Q plus P. This is valid. This is valid. You know these from properties of functions in pre-calculus, correct? Now, what about the zero object? It is the zero polynomial, correct? So you have it. What about here, U and negative U? If you have a polynomial, Px equals A plus Bx plus Cx squared. All you need is just to take negative A minus Bx minus Cx squared. Add them. What do you get? 0. So it is valid. What about this? Closed under scalar multiplication. Take a polynomial and multiply polynomial of degree at most 2 and multiply it by k. What do you get? You still get a polynomial of degree at most 2. So number 6 is valid. Number 7, add 2 polynomials, then multiply by constant. That is the same as if you multiply each one of them by that constant, then add them. This condition, this condition, this condition, all of them are satisfied. So this is a vector space. It is a vector space. And this vector space, we call it P2. Let me here use this color. P2. Okay? Now again, let's develop this further. What if I come to this and I change it and I make it instead of 2, 1, or I make it 3, or I make it 4? Or if I make it n. So here, it will be an xn plus an minus 1 xn minus 1 plus a1x plus a0, such that those coefficients are real numbers. And the same addition, the same scalar multiplication, then this is a vector space and we call it Pn. So here you have another family of vector spaces. It is called Pn. Those vector spaces, we are going to keep using them. So you need to keep this notation in your mind. M, P, R. Okay? All right, I have a question for you here. What happens if I don't put restriction here, n? If I just take all polynomials, put them in one set, call it V, and addition of polynomials or addition of functions and multiplication of a function by scalar. Is that still a vector space? Well, you go over the same conditions. All the conditions are satisfied. Yes, we call it P infinity. So you can say this is separate example. This will not talk about it too much, but maybe once in a while we mention this. However, Pn, we are going to talk about it a lot. Okay? All right, so here we have family of nice examples. Let's take more examples, but now let's make them kind of more fancy. Here is another example. I'm going to take V to be the positive real numbers. Okay? I want to define addition as follows. U plus V to be UV. So how do you add? You multiply. And the multiplication by scalar as U exponent k. So here, define this. We want to define the two operations in this way. Why? Just for the fun of it. You know, we want to get you out of the trivial, out of the simple, and here, let you get out of the box and think about something that is more sophisticated. Okay? So here, if I tell you here what is 2 plus 3? What is 2 plus 3? Don't tell me it is 5. It is 2 times 5. Okay? What is 3 multiplied by 5? Don't tell me it is 15. No, it is 5 exponent 3, and that is 1, 2, 5. Okay? We want our operation to do this. Is this a vector space? Is V with these two operations a vector space? It is becoming interesting here. Look at it. Well, some of those conditions, they are going to be valid, kind of trivial, but some they are not. So if you think about the first one, we are talking about positive real numbers. So this is going to become multiplication. So if you multiply two positive real numbers, what do you get? You get a positive real number. So the first one is valid. If you take the second one, u plus v, well, that is going to be uv. But you know, in multiplication, this is still valid. So this is valid. This is valid. This one is tricky. Number 4. So let's focus on number 4. So 1, easy. 2, easy. 3, easy. Number 4. The zero object. Something, when you add it to u, you get u. What is that? Think about it. So here we want something, you add it to u or to v, we want to get v. So what is this? It is the number 1. Because 1 times v is v. So here, your zero object is going to be the 1, the real number 1 is the zero object. This is the zero object. Okay? Number 5. For each u, there is a negative u. So what is that going to be? 5. 5 is tricky here. U plus what? We get the zero object, which is 1. It should be the reciprocal of this. So when you multiply, you get 1. So that is going to be 1 over u. Now, is the reciprocal here? Yes, if you take a positive number, then the reciprocal is also a positive number. So yes, here, this 1 over u will do the job of negative u. So here when I say 1 over u equals negative u, I mean by that it will do the job of negative u. Okay? So yes, we have it. So number 5 is satisfied. What about number 6 here? Ku. Ku is going to be u exponent k. U is a positive number and k is the real number. Number 6. Ku is going to be uk. This is a real number and this is positive number. So positive number is to the exponent something real number here. What you get a positive number. So this belongs to your v. So that is valid. What about this one? Ku plus v here. So that is going to be what? Number 7. I will clarify number 7 and I'll leave the rest for you. Number 7. So k into u plus v. You know, when you have parentheses, you need to do what is inside the parentheses first, correct? Correct? So here, which one you do first? You multiply or you do this first? You do this first. Now this is going to be this. So this will be k u v. Now, k u v is going to be u v exponent k. And you know this will be u k v k. Correct? Now, go back. What do you get? This is u k plus v k. Now, what is this? This is, go back here. This is k u plus k v. Okay? So look here. I mean, the way we write it is tricky. Okay? Number 7. Number 8 and 9 and 10, I'll leave it for you. So if you understand number 7, number 8 and 9 and 10 should be easy for you to check. So here, all the 10 conditions are satisfied. So this is indeed a vector space. Yes. And you can check the 10 conditions one by one. Okay? All right. Now I want to make it kind of twist it a little. Instead of saying positive real numbers, I am just going to write non-negative real numbers. So here I'm going to remove this. And I just say here x such that x is larger than or equal to 0. I am going to include the 0 number in my set. Is that going to be a vector space? Go over those and see which one is still valid, which one is not valid. You can observe right away that you have a problem when you talk about the reciprocal, correct? Do you remember when we talked about the reciprocal here? U, 1 over u. If 0 is there, then you cannot talk about the reciprocal. That is a problem. So right away you can see number 5 is not valid. Okay? So this, if you do this, that will ruin your vector space. If you add 0 to this set and you keep those operations, that will ruin your vector space. It will not be vector space anymore. Okay? All right. We have a few more interesting examples. I'll leave it for you in your exercises. You have some examples about, for example, if you take all continuous functions and you put them in a set, all continuous functions, and you define your addition to be addition of functions and the multiplication to be multiplication of functions by scalar. The 10 conditions are satisfied. Okay? So you are going to find in the exercises you have a bunch of examples other than those, and I'll leave it for you to do it yourself. All right, after this, I'm going to talk about this nice idea. Subspaces. So here, you have a vector space. You check the 10 conditions, you have a vector space, it is nice, lovely, you do your business here, you are fine. Okay? But now, I want to bring smaller bag, in some sense, here. And I'm going to give you a shovel here. And you start taking something from here and put it here. Okay? So, it's like when you go to buy something, you start to take and put in your bag. So you took something from here, you put it here. Okay? Now, here, you keep using the same addition, the same multiplication. So this, let's call it S. With S, I want to keep using the same addition, the same scalar multiplication. Okay? Now, is what you take here by itself a vector space? That is the interesting question. Is it by itself a vector space? Well, if you think a little bit about it, it may be a vector space, it may not be a vector space. For example, if you do not take the 0 object, if the 0 object stays here, you don't take it here, this is not going to be a vector space, correct? Okay? So that takes us to another interesting question, which is, okay, I need to guarantee that this is a vector space by itself. So what should I do? Should I check all those 10 conditions? We need S plus, or with those two operations, to be a vector space. We are not interested in something that is not a vector space. Okay? So what we take, we want to guarantee it is a vector space. Okay? So in that case, what should we do? Well, let us go over those 10 conditions one by one and see which one do we need to check and which one is going to be inherited. Some of those are going to be inherited. We are going to get them free of charge. So for example, the first one, u plus v. So if you take two vectors here and you add them, is the result going to be an s? Or maybe you did not take it. So that is not obvious. That we need to double check here. What about the second one? Well, if they commute here and you take them, still they are going to commute here. Correct? So basically the second one is going to be inherited. I don't need to worry about it. What about the third one? The third one is going to be inherited. If it is valid here, here still it is valid. The zero object. Did we take it or we did not take it? That is not obvious. Number 5. For each u, there is a negative u. Well, when we took u here, did we take also negative u with us? That is not sure. Number 6. U, k, ku. So when you take here u, does it mean you took all scalar multiples? That is not sure. What about number 7? Number 7 is going to be inherited. If this property is valid in the mother space, now here it is going to be valid in this new space. Correct? So this is going to be inherited. Number 8. Well, if this happens in the origin, also it happens here. So there is no problem. It is inherited. This is inherited. This is inherited. All right. So here we have 1, 2, 3, 4 that we need to focus on. Well, let's again revisit them and focus again on those. Now, this one, that is crucial. We have to check it. And this one is crucial. We have to check it. Let's think about this and this. Now, if we guarantee this one, and I take my k to be -1, isn't that going to give me this condition? So number 6 here, it comes hand in hand together with number 5. So if I guarantee number 6, number 5, I get it free of charge, and in that case, I don't need to worry about it. Well, the result is the zero object. The zero object is here in number 4, so I need to guarantee that. So here, this and this will guarantee number 5. It's like buy one, get one free. And in that case, it narrows down to those 3 conditions. In fact, this one, I don't need it. If I take k to be 0, then 0u is in V, and 0u is 0. So basically that I don't need it. However, I need to guarantee that my set V is non-empty. So this one, I can just say instead of this, or make sure S is not empty. If S is not empty, then this one, you get it from here, and you are fine. So basically, it narrows down to 2 conditions, 2 major conditions, together with either the zero object is there, or you need to guarantee it is not empty. Okay, so here, number 1, we need U plus V in S for all U, V in S. Number 2, you need KU belongs to S for all K in R and U in S. And maybe this one I should put it first. We need the zero object to be there, or S is not empty. Maybe this one you should do it first. Because before you start, you need to guarantee that your set is not empty. It is not, you are claiming that you took something, but this is empty. In that case, why do we check those conditions? Okay, so those are the three conditions that you need to check to guarantee that this is a vector space. If this is a vector space, in that case, we call it a subspace because it is coming from this mother space. Okay? So it is a vector space by itself, but because it is coming from this vector space, we call it a subspace. Okay? Let me give you one example here, and next time I'll give you more examples. Okay? So now we don't need this. Example. I'm going to take my V to be M2 by 2. All 2 by 2 matrices. And I'm going to take my S to be all diagonal 2 by 2 matrices. Okay? So here, S is going to be this set, set of matrices. Is S together with matrix addition and scalar multiplication here is a subspace of M 2 by 2. Well, as I said, why don't you check this first? The zero object. What's the zero object here? The zero object is the zero matrix. So if I take 0, 0, 0, 0, is this a diagonal matrix? Yes, it's a diagonal matrix. So here is number one. The zero object belongs to S. So it's not empty. 2. You know, guys, some people, they like to combine this and this together. U plus VKU and write them like this. Let U equals A1, 0, 0, B1, and V equals A2, 0, 0, B2. Now, U or V plus KU or U plus KV is going to be this plus K. So this is going to be A1, 0, 0, B1 plus K, A2, 0, 0, K, A, B2. And that is A1 plus K, A2, A2, 0, 0, A, B1 plus K, B2. Here, B1 plus K, B2. Well, if you look at this, this is again a diagonal matrix, so that's it. Okay, so basically here you can combine this and this in one condition and check it as I did here. That is absolutely fine. Okay, it's like you catch two birds with one stone. Okay, instead of writing that twice. So again, diagonal matrix, diagonal multiplied by K. When you add them, what you get a diagonal matrix. So yes, this is a subspace. Okay, so that is a very simple subspace. All right. What if I change this and I make it, instead of all diagonal, if I make it all upper triangular? What do you think? Upper triangular. still you are going to find it is a subspace. I'll leave it for you as an exercise. Okay? Change this example. Instead of diagonal, just take it upper triangular or lower triangular. Okay? You are going to find it is still a subspace. All right. Well, let me give you just a few conclusions or a few remarks. If you ask yourself when you do this, what is the smallest vector space you can take here? You want to take as less as possible, but you want to guarantee this is a vector space. So what do you take? Just take the zero object by itself. If you take the zero object by itself is going to be a vector space. All the 10 conditions or all the 3 conditions here are going to be satisfied, and that is called the trivial subspace. The trivial subspace. Okay? The trivial subspace. What else? Something easy that you can take right away. If you take the whole vector space, if you are kind of greedy and you take the whole vector space, S is V. It is obviously a vector space, and it is a subspace of itself. Okay? So those are the most trivial subspaces you can form. The zero object and the vector, the whole vector space. Okay? Okay, I gave you many examples or some examples about subspaces. Can we take an example in which it is not a subspace? So let me go back and change this one and see. Take V to be R2. Take S to be AB such that A plus B is 1. This set belongs to this vector space. I'm going to use the same addition, the same scalar multiplication. Is this a subspace by itself or a vector space by itself? Is S a subspace of V? Remember, what was the first condition that you need to check? Either it is not empty or you need to guarantee the zero object is there. Is the zero object there? 0, 0. The zero object here is 0, 0. Is it there? 0 plus 0 is not 0, correct? So that is no, because the zero object does not belong to S. That's it. Just one sentence. Okay? So here, let me call this S1, S1. Here, let me take S2 to be AB such that A plus B is 0. So I twisted this a little now. Is that a vector space or a subspace? Is S2 a subspace of V? Well, now the zero object is there. So number one here, the zero object belongs to S. So that is not a problem anymore, correct? Now, what about the other two conditions? So if I add here if I take two vectors from here and I add them, is the result going to be here? Well, if you think about this, here, S2, you can understand it better just by saying S2 is in fact going to be A, and B is going to be negative A, such that A is a real number. If you write it in this way, you can see that if you take two vectors of this type and you add them, the result will be of this type, correct? So here, number 2, if you take U to be A1, negative A1, and you take V to be A2, negative A2, and now you take U plus KV. What is that? That is going to be A1 plus KA2, and here negative A1 plus KA2. Yes, it is of the same type here and the negative of this. So this belongs to S. So yes, it is a subspace. Okay? In fact, such this subspace is nice. You don't need to check those conditions. You can see it right away when you write it like this. S2 is in fact A multiplied by the vector 1, negative 1. And this, we call it a span of this vector. So you take this vector and you take the span of that. What is the span of that? Basically all the stretches and shrinks of that vector. So you take a vector and you stretch it as you wish, you shrink it as you wish, and the result you put it in one set. So we call this the span of this vector, okay? Or all linear combinations of this vector. This, right away when you see span of some vectors, these conditions are going to be satisfied without trouble, okay? So we can say this span, look, this is a span of this vector. Okay? In that case, it is obviously a subspace. And later on, we are going to take more examples about that and see that if you can write your set as a span of some vectors, right away the conditions are satisfied, and then you don't need to do much work. All right, so that's it for today. Thank you for listening, guys. And next time, I'll talk more about subspaces, about span, and then we go deeper to characterize properties and certain characteristics of our vector spaces and subspaces. All right, so I'll stop the recording now. Thank you very much. See you later.